Next, what we are going to discuss is a theoretical analysis of time efficiency. The running time T for an input size n is measured based on the executive time taken for the basic operations in an algorithm and the number of times the basic operation is executed for the input size. This is what the simplest mathematical form, the time efficiency for an algorithm is. T of n is approximately equal to the execution time for the basic operation of the number of times the operation is performed for an input size. The input size and the basic operations for any particular problem can be tabulated based on this format. The input size measure and the basic operation. So if you are searching for a key in a list of n items, so the input size is actually n. The multiplication of the two matrices, the row, number of row and the number of column, it's an input size. Checking the primality of given integers, it's a number of digits in the given number. Typical graph problem, that's based on the number of vertices and the edges. The basic operations are the key operations that we do in an algorithm. We do, if it is a searching means, we'll do a comparison. If you are doing a multiplication means the multiplication operation that will be performed between the numbers. And when we are checking the primality of a given number, the division is performed. And when it is a graph problem, the visiting the vertices and visiting the nodes or the traversing an edge is the basic operation. So based on these input size measure and the basic operation, the time complexity is being calculated. Empirical analysis of the time efficiency. First, select a specific sample inputs. Use the physical unit of time that we count the number of basic operations for executions. Then we analyze the empirical data. Here we can see a type of formulas for the basic operations count. C of n is equal to n into n minus 1 divided by 2. So n is a number of times that particular, it's a number input size basically. So n into n plus 1. So that is the main loop as well as a sub loop. Recursively, the function gets, the operations gets invoked. Formula indicating the order of the growth with a specific multiplicative constant. Say for example, 0.5 is a constant. It gets multiplied with n squared. So n squared is 2 times the for loop has been iterated. And every time it's n iterations. the basic operations are performed n square times totally, since there are two loops, one inside the other. Formula indicating the order of the growth with the unknown multiplicative constant is Cn squared. The same thing. So here it is, we said specific multiplicative, here we said unknown multiplicative component. Then the order of growth with a constant multiple, if the n becomes infinite, if n becomes infinite, how much faster will algorithm run on the computer? Is it twice as fast, or is it not solvable? This is the order of the growth. How much longer does it take to solve the problem of the double the input size? Here we can see some iteration of values. The n values 10, 100, thousands, 10,000s and so on. For that, the execution time of the various measures like n squared, it's exactly the exponential is raised by 1. 10 means 10 power 2, and 10 power 2 is 10 power 4, 10 power 6 is 10 power 12, and it is 3 times 2 multiplied by n, n factorial, n into n minus 1 into n minus 2 into up to 1, n log n, log n, log n base 2 multiply with n time, log n time. So as we compare to it, so log n is the quite minimal, what can say, the value as compared to all n, n log n, n squared, n cube, 2 power n and n factorial. So for every algorithm, the efficiency depends with the input. So there could be three cases that's possible: average case, best case and worst case. Worst case is when the maximum input is maximum over input size of n. So the execution time is getting more. Best case in the sense minimum over in the input size of n. Average case is the average of over the input size of n. So C is the cause that's measured. So it could be average, best, worst, depends on the input n. So number of times the basic operation that gets executed on a typical input. So that's what the basic measure for the efficiency, not the average of the worst and the best case. Expected number of operations considered as a random variable under some assumption about the probability distribution of all possible inputs. Let's look at a simple search algorithm. Algorithm name is given. This is the input parameter what it's been supplied to this particular algorithm. A is an array, a list is having the values 0, 1, 2, 3 up to n minus 1. So there are totally n values are there. K is a value to be searched for. So what's the first thing that's going to be done? These are all the comments for our understanding. Searches for a given value in a given array by sequential search. An array of 0 to n minus 1 and a search key k. The index of the first element of an array that matches the k or minus 1. If there are no elements matching, then it will be returning minus 1. I is initially 0. While I is lesser than n and a of I is not equal to k, then in both the condition we increment the I. If suppose I is greater than n, and a of I not equal to k, so one condition becomes false, automatically the loop exit and comes to the if statement. Suppose if the value I is less than n, but a of I is equal to k, so then also the condition is false and it comes out, then again it comes to the statement if, the if statement. In the if statement, is the condition is if I is lesser than n, it returns I. That means in that particular position, the value is found. Else it's going to be -1 because I is already greater than n and nowhere a of I is equal to k. Now, here we do have a worst case, best case, as well as average case. That depends on whether the input is found in a list or the input is not found in the list. The probability of successful search is equal to 0 lesser than or equal to p lesser than or equal to 1. It's a probability value. In always the probability value lies between 0 and 1. The probability of the first match occurring in the ith position of the list is same for every I. So the probability of the first match occurring in the ith position of the list is p over n for every I, and the number of comparisons made will be I. For an unsuccessful search, the number of comparisons is n, with the probability of such a search as being 1 minus p. If it is a successful search, if p is equal to 1, the time, what is the time taken for C average of n? And if it is a unsuccessful, what is the time taken for the C average of n? If it is a successful search, the average of n is going to be a how in which particular position that particular value has been found. But is unsuccessful, it's not at all found. So even the list is longer. So that's going to be the time. That's going to be the worst case of it. The asymptotic order of the growth, a way of comparing the functions that ignores the constant factors and small input sizes. This is very important. The previous examples we saw 0.5 and some constant we try to multiply with n squared. So usually those kind of the constants are neglected in terms of calculating the execution time. Big O of g of n, the class of functions that grow no faster than g of n. And O of g of n, the class of function f of n that grow at same rate of g of n. Omega of g of n, class of function f of n that grow at least as fast as g of n. This is what the asymptotic growth, order of the growth of the functions. What's this big O? The function t of n is said to be a big O of g of n, denoted the T of n belongs to big O of G of n, if this T of n is bounded above by some constant multiples of G of n for a large number n, that is, there exists some positive constant C for some non-negative integer n naught such that T of n is lesser than nor equal to Cg of n for all n greater than n naught. Say for example, 10ns big O of n squared, 5n plus 20 is big O of n. So if you say 5n plus 20, we are multiplying 5 with n and adding 20. So some constant multiplication and addition happens. So that value is neglected and we are writing it as a big O of n. Look into this curve. The T of n belongs to big O of G of n. So when T of n is lesser than, in all time, T of n is lesser than big O of G of n. So then the big O notation is actually drawn like this. An exponent based on the size of the input increases, the execution time increases. Big theta of G of n. A function is said to be a theta of G of n if T of n is bounded both above and below, like this. If there exists some positive constant C1 and C2 and some negative integer n naught, say that half n into n minus 1 is lesser than or equal to half n squared, whereas half n into n minus 1 is greater than or equal to 1 by 4 into n squared. So the corresponding curve is drawn like this. Third is a big omega. A function T of n is said to be in big omega of G of n if T of n is bounded below some positive constant multiples of G of n for all large n. There exists some positive constant C and some non-negative integer n naught such that T of n is greater than or equal to Cg of n for all n greater than or equal to n naught. So for example, n cube is greater than or equal to n squared. Cg of n and T of n. Some properties of asymptotic order of the growth. The T of n belongs to big O of f of n and f of n belongs to big O of G of n if and only if G of n belongs to omega of f of n, and if f of n belongs to big O of G of n and G of n belongs to big O of h of n, then f of n is equal to big O of h of n. Try to understand this reflexive growth from this function. If f1 of n belongs to big O of g1 of n and f2 of n belongs to big O of g2 of n, then f1 of n plus f2 of n is equal to big O of max of g1 of n comma g2 of n, whichever is the maximum, that's considered as a summation of these two functions. Here is a limit t of n divided by g of n, n moves to infinity, either it could be 0 or c greater than 0 or infinity. It is 0 order of the growth of t of n lesser than order of growth of g of n. It is c greater than 0 order of growth of t of n is equal to order of growth of g of n. Order of growth of t of n is greater than order of growth of g of n. 10n versus n squared, n into n plus 1 divided by 2 is versus n squared. This is what the establishing the order of the growth using the limits. Basic asymptotic efficiency of the classes based on this. It's n factorial for a factorial. 2 power n is for an exponent. N cube is for cubic, n squared is for quadratic. N log n is for the log n. N means a linear, log n is logarithmic, 1 is a constant. That's it. The next class we see the mathematical analysis of the non-recursive algorithms. Thank you.